welcome to a video on the principle of conditionalization. So let's briefly recap where we're at in terms of the probability portion of this course. So we've introduced unconditional probability so far, which recall is a function that assigns real numbers to statements as a measure of epistemic probability, that is, a measure of how likely an agent judges a statement to be true, right? So this was unconditional probability. Corresponding to epistemic probability. And, right, it was a function, right, from statements, right, we had an algebra generated from a set of simple statements to the real numbers, right? And we said that this had to be governed by three key axioms, right? The axioms of normality, non-negativity, and additivity. And we've explored a number of consequences of these axioms. Right? We've also introduced the notion of conditional probability. Right? Conditional probability. And we've introduced this as a measure of inductive probability. That is, right, how likely one statement is to be true given another statement. Or we were thinking in terms of arguments, so sets of statements, but we can always view the premises as an argument. If we wanted to, we could associate them with their conjunction so that it becomes a single statement. Right? So this inductive probability. And remember, this was a function that assigns real numbers to pairs of propositions, right? So we wrote it like that with the line, and right, it takes as input two, right, an ordered pair of statements. One that we're going to assess the probability of, and the other that we're going to assess the probability of the first in light of, right, or that we're going to assume to be the case. Two real numbers. Okay, and we said that conditional probabilities should be related to unconditional probabilities by the ratio rule, right? We have the ratio rule. This is our key constraint here. And from this, we were able to prove various results regarding conditional probabilities, including, perhaps most importantly, Bayes' theorem, right? So show that all the axioms probability together with the ratio rule led to Bayes' theorem, which gave us a nice way to compute what some conditional probabilities are. Now, all of this discussion so far has remained static in nature, right? We've been looking for probabilities and conditional probabilities at a time, right? But sometimes a person's probabilistic judgments change, right? Sometimes they evolve over time. Now, what we want to ask in this video and the next is, are there any principles that govern how probabilities should change over time as people have new learning experiences, right? That is, we want to know, right? Suppose you start off with some old or initial probabilities, and then you have some sort of experience, right? How should that translate into new probabilities, right? That's the question we want to ask. Now, a big issue here is going to be, how do we cash out, right, experience, what it is to have a learning experience? Well, in this video and the next one, we're going to look at two proposals for how to model learning experiences, and corresponding to each of these ways of viewing experience, we'll have a proposed rule for updating or changing your old probabilities into new probabilities in light of that experience. In this video, we're going to look at the most famous model for updating probabilities, and that is conditionalization. All right. In the context of conditionalization, we view learning experiences as corresponding to propositions. So in this way, we're thinking about there being sort of a mapping between possible experiences and propositions. And the question is, how should I revise my probabilities if I learn a new proposition to be true? Okay, so let's state what the principle of conditionalization is. Conditionalization. Okay. This principle says that if you start out with epistemic probabilities that are represented by let's write it as P sub old, right? Those are your initial probability judgments, right? And then have a learning experience that's captured by a proposition. We'll say E. Then, right, this up, then your new probabilities, right, which I'll write as P sub new, right, should be equal to your old probabilities conditional on the proposition that you just learned, E. Okay? So this is what the principle of conditionalization says. Now this makes some sense in light of the way we proposed connecting epistemic and inductive probabilities early on in this course. Right? We can view a person's epistemic probabilities in a proposition X as corresponding to their judgment of the inductive probability of an argument that consists of all their knowledge as premises and has X as a conclusion. Well, then it makes sense that if I learn a new proposition, then I'm adding that to my stock of knowledge and changing my epistemic probabilities to reflect the inductive probability of an argument with the broader stock of knowledge as premises. All right, so this gives us a way to change our beliefs or change our probabilities in light of new evidence that can be captured as a proposition. Now let's consider an example of how this would work, and it will also give us some practice using Bayes' theorem, which is good for the homework and exams and such. So this will be a coin example. Okay. Now let's suppose that there's a coin that can be flipped, has two sides, heads and tails. And let's suppose that the coin is of unknown bias, but I do know that the bias is of only one of two possibilities, right? My first hypothesis is that the bias of the coin is 1/3 towards heads, right? 1/3 toward heads, right? So this means that the probability that it lands heads if you flip it is 1/3. Probability that you land tails if you flip it is 2/3. And let's say the other possible hypothesis is that the bias is 2/3 toward tails. Or excuse me, it's 2/3 towards heads. So 1/3 towards tails. Right? Now these are the initial two possibilities I consider, H1 and H2. And let's suppose that initially, and I'll write this with P old, initially my degrees of belief are such that I think these are equally likely to be true. So I say probability of H1 and probability of H2 are both equal to 1/2, right? Each is as equally likely to be true as the other. Now let's suppose that you flip the coin and let's say it lands heads, right? Then that's an experience that I have, a learning experience that we can capture with the proposition. That we can capture the proposition, I'll say little h1, right? This will be the statement that coin landed heads when we flipped it the first time. The coin lands heads first. All right. Now, right, you've had a learning experience where you've learned that the coin lands heads first. What should your new probability be in the hypotheses, right? Like the hypothesis that the coin is 1/3 biased towards heads, or the hypothesis that the coin is 2/3 biased towards heads. Well, we can employ the principle of conditionalization here. So we can say that my new probability, and let's look at the first hypothesis, H1. My new probability in that should be equal to my old probability in that proposition h1 given the proposition that I just learned, which is little h1, right? But we can use Bayes' theorem to find the value of this conditional probability, right? So let's do that. So it would be the probability of little h1 given big H1 times prior probability big H1 all over same thing. First in the denominator, probably little h1 given big H1 times probability of big H1 plus the probability that I would have seen little h1 given big H2 times the probability of big H2. And these are all values that we should know, right? Probably that you'd see little h1 given that the bias of the coin is 1/3, of course, towards heads would be 1/3, times 1/2 is the prior probability of that hypothesis, over same thing for first, 1/3 times 1/2, plus the probability you would have seen little h1 given the second hypothesis is 2/3, because that one says there's a 2/3 chance of heads, times the prior probability of that hypothesis is 1/2, right? So we can compute all this out. Let's see, so on top we have 1/6 over on the bottom, that's 1/6 plus 2/6 is 1/2. So we get 1/6 divided by 1/2 is 1/3. So my new probability in the first hypothesis, namely that the coin is skewed towards tails, right, and only has a 1/3 bias towards heads, has actually gone down. It's lower than what it was originally. Originally it was 1/2. Now my new probability is 1/3 in light of this new evidence I've received, which makes sense because, right, if the coin lands heads more than tails, that's more evidence that the second hypothesis would be true rather than the first. So this is sort of what we would expect. Right? So this gives some example with both employing Bayes' theorem to find a conditional probability, and then using the principle of conditionalization to realize what the connection between your new probabilities and your old conditional probabilities should be. This is definitely a principle that we'll employ on some of the homeworks and exams going forward. In the next video, we're going to look at another model of updating or changing our probabilities over time for cases where our learning experience may not correspond to learning a particular proposition with certainty. So we'll look at that in the next video. Please remember to complete the participation poll for this video, and I'll see you next time, guys. Thanks.